Thanks very much. So I had the enviable job of coming to speak to you today, which was a great pleasure. I asked Mike Lafferty, well, what would you like me to talk about? He goes, oh, just say what we're working on this year at Intel in 15 minutes. Pretty tough to do. And without a legal disclaimer for those of you who've sat through our NDA presentations. And there was great rejoicing. So actually, the first thing that we're working on, and the most important thing, I think, is trying to enable science. And at Intel, one of the problems that you end up having is you think about microprocessor, you think about what you're trying to build, or I'll spend a lot of time on where my personal passion is. But ultimately, the thing that makes us most excited is the publications, the science, the discovery that ends up coming out of the work that we're doing. And frankly, there's both a personal motivation, it's cool, but there's a professional motivation. The more discovery we make, it actually generates more discovery, and it's actually remarkably good for business. Each one of these cases I cited up here was an at-scale use of the Xeon Phi processor. As Mike mentioned last night, I was the planner, launcher, and have been kind of one of the principal drivers of what's become the Intel Mic architecture, and so we love counting them. But first and foremost, one of the things we have to remember about Intel is that we talk about microprocessors or fabrics or what I'm going to talk about, which is code modernization, but at the base of Intel is a wonderful manufacturing company. And what we build are some of the world's smallest, most energy efficient and highest performance transistors. And then we combine them in as many unique ways as we possibly can. First and foremost for the next year, what Intel is going to be working on is 10 nanometer and 7 and past that. So really the things we're working on are trying to build those energy efficient transistors and then figure out wonderful things we can go do with them. And in the case of high performance computing, we had out of hell with it. We had one of these moments at a roundtable much like this back in Portland, Oregon in 2009 when we talked about our microprocessor roadmap, and our customers came back to us and said, do you guys get it? It's not about the CPU. You keep talking about CPUs and features and instruction sets and all. That's not what it's about. We have to take a look at the entire system and how systems are going to scale. We're hitting the memory wall. Fabric's not scaling. What are you guys doing about that? 6 years later, I'm happy to report that across all of these areas, whether you're taking a look at Omnipath Fabric, which was mentioned earlier, or taking a look at power efficiency at the transistor or the systems level, looking at resiliency, scaling machines to, we've already proven that we can do millions of cores in a single machine. Taking a look at processor performance, the Intel Mic architecture has come about since that comment. The talk about Knight's Landing with its integrated memory, all of these are actually very tangible measurements of taking feedback and trying to fundamentally change what we're doing to be able to look at things systemically and provide performance that enables those kinds of discoveries. And we'll be working in all of those areas. Now, two tangible things we're going to be doing in the course of this year. We have two major products that are coming into the high-performance computing segment from our group, and first, of course, is Knight's Landing. And there's been a lot of news on Knight's Landing and the future generation of that, Knight's Hill, with the announcement of Aurora that went on earlier this week. And I see Katie's over here, the folks from NERSC, who have talked about the Quarry system that will be coming online, and a few other very large systems that will be built on top of the Intel Many Integrated Core architecture. Knight's Landing is a breakthrough for us in a lot of ways. It's the first fully bootable, highly parallel processor. It builds on top of some of the things we've done with Knight's Corner, but it gets rid of some of the offload constructs, and it builds a fully IA-compatible microprocessor. But much more importantly, it starts to address the memory wall, and it scales very well on the path towards exascale. So as we've got the next several generations of the product line will help get us there. So we're very excited to get this, think of it as a high-performance computing system on chip with fabric, memory, microprocessor, all for the first time built into a single device and package. And then secondly, our Omnipath Fabric, which not only will we be talking about the high performance that it ends up delivering, but based on the way the switch design and looking at things systemically reduces the cost of even small clusters through higher radix switches and different levels of scaling. So, faster, cheaper, and more scaling out of it. Both, pretty good recipes for success. So we're going to be focused on finishing up those two products and getting them to market. But I'm not going to spend most of the time today talking about products. Hopefully, every one of you has an Intel sales rep or somebody who's come by and talked, and you've got the NDA roadmap and you know what we're doing. If not, if you're an Intel employee, Dennis, Mike, put your hands up, and we're here to answer questions on the roadmap more or less while we're here. Don. So there's quite a few Intel folks here to help. I wanted to talk about what we're really up to this year. And what we're really up to, I think, is trying to do something transformative in software and in the ecosystem. Now, this is the first and only chart that has a legal disclaimer on it because I'm going to quote a performance number. This happens to be from a bank in New York, and it is an actual application that they have running, in this case, single precision binomial options pricing. And what you have on the line is from 2007 with the Xeon processor Harpertown through Haswell. The different scaling that actual application gives, the bottom line, the dark blue line, is what the bank has actually seen. The performance of the application over 7 years has actually doubled, which is good if over 7 years, for free, more or less, I doubled my performance. But if you move it to vector, the light green line, that was simply by using the SIMD that was in the processor. They could have had that light green line the entire time. What's shocking, or was shocking to the bank, is the yellow line. And that is what happens if you use all the cores, all the threads, and all the vector units. It actually measures out to be 179x in performance, or in practical terms, the ability for a trader to actually be running the risk analysis in real time while trading, rather than doing things overnight and coming back in and rebalancing the books in the morning. It changes the way you work. And the really cool thing from an Intel perspective here is I don't have to sell you a single piece of hardware in order to get that. That's the performance that was laying on the table. Now, admittedly, anything that has to do with Monte Carlo has some unique attributes. It's a flat profile application. It's got a single hotspot. It's insanely data parallel. It's a poster child application for making these kinds of points, but that's why I chose it. Even so, we see very commonly 6 and 10x increases in performance in scientific applications, same hardware to same hardware. Now, why I worry about this, on the one hand, you could say, well, hey, Intel, you're just going to sell a lot more microprocessors if we don't fix this. But as we look at the power wall, as we look at the practical size of systems that we can build, as we look at the amount of science we're not getting done, or the amount of discovery we're missing because we're not fully utilizing the microprocessors, it's a problem. And since we're building a roadmap that is going to continue to drive parallelism, it's also an opportunity to really get our applications ahead of the machines we're going to be building. Well, we can't do that alone. It's funny, we've seen through conversations, both at networking events as well as through these presentations, no one company, institute, not the NSF, not the DoD or DOE, can actually hit the broad range of applications that one needs to be able to move from parallel to modern and parallel. So we've partnered pretty broadly. To some degree, we've put our money where our mouth is, but far more importantly, we've put our technology, our engineering, our time into developing algorithms that scale, or helping people work on their codes to scale to fully thread and fully vectorize and fully use the memory available inside our systems. And this happened to be a group of the partners. We've actually created something called Intel Parallel Computing Centers. It's a program. We're up to 60-some global institutions who are looking across really all domains of science. And what we're doing is we'll contribute a little bit of money, but technology, hardware, knowledge, programming, and put that into one end of the system. What we're looking out of that is code, community codes, help from publications, PhDs, new teachers, in order to create a virtuous cycle of new people to be able to work on applications going forward. So we've been trying to contribute that. If you haven't seen, I'll show some books and things that we've published that we've put into the public domain on that. So a vast majority of our time, and one of the highest priority things, is not just getting products we can sell, but trying to address the code modernization opportunity for us. Another example, and I was pleased to see how many people were talking about visualization in their presentations this week. Another thing that we've contributed recently to the community that you may not have heard of is 2 alpha products, both a software visualization renderer for OpenGL, as well as a high-performance ray tracing renderer that can work under ParaView as well. And these are some examples. Dan may recognize one of his machines in the background. That's actually a ray-traced image of a Florida International CFD model of flow through stone, which is fully visualized up on the, Maverick, I keep getting my Texan animals confused, but up on the Maverick rendering cluster. But it's all being done in situ and put up on top and put up onto a single display, ray-traced. So we put out 2 different websites. One is something called openswr.org, OpenSWR. That's an open source OpenGL renderer. You can see a picture of the Wendell Horton plasma model, which is being rendered under ParaView. But we support most of the main visualization software applications today. What's really remarkable is by rendering in situ the performance that we're able to deliver by not having to simply move it over to a separate render cluster. All of this we're continuing to work on and bring out into the community. It's an example in something you wouldn't think of from the CPU or from Mike, but actually is actually quite wonderful. We'll hope to have the beta out by the end of this year and have it as a product. There is actually an open source group that are picking these up and trying to make them into full-time projects. Well, lastly, what we're working on is we spent about 3.5 years enabling Xeon Phi and getting to those wonderful articles about performance, but we're trying to write it all down. And we're trying to write it down both in scientific papers, academic papers, but source listings, and then publishing in every possible way we can, everything from structured parallel programming, how to think parallel, to how the hardware works, to how to layer software on top of the hardware, and then going all the way to specific examples. The last book that we did called High Performance Parallel Pearls takes about 30 case studies where we go from the domain science problem, the mathematics, the algebra, the code, the measurement of the code, the performance issue, and then the computer science techniques used to get vectorization or improve memory performance or to solve performance problems on Knight's Corner. So one of the things we're trying to do is write everything we can down. And every single case study from either the Xeon Phi or the Parallel Pearls book is up on a site called lotsofcore.com with complete source listings. And every chart or graph that we've created is open to the public too, as well as a teaching example.